Well, now that I've used the word isotopes about 3,000 times in the previous presentations, I'm going to actually come along and define the term isotopes. Hopefully you've gotten some familiarity with the term in my usage of it. We're going to define isotopes, and then we'll use that to define what are called radioisotopes. And then radioisotopes leads us into the concept of electromagnetic radiation. That's where the radio and radioisotopes come from. And so those are the next three objectives, 11 through 13. So in the next three objectives, I'm going to be talking about isotopes and radioisotopes and electromagnetic radiation. So isotopes are what we saw earlier, and as I mentioned earlier, isotopes differ not in the number of protons and not in the number of electrons, but rather only in the number of neutrons that an atom has. Remember that the number of neutrons doesn't change the charge of it, because the neutrons have no charge. All it does is change the mass. So these are atoms of an element that have the same chemical properties because they have the same number of electrons. They have the same atomic number because they have the same number of protons, but they have different numbers of neutrons, and so they have different atomic masses. A good example that we can start with is the idea of hydrogen. And hydrogen, it turns out, exists in three isotopes, two that are found in nature and one that's man-made. The first one and the most familiar one and the most common one that we saw was one proton, one electron, so an atomic mass of 1. We call that hydrogen 1, and so that's an isotope of hydrogen. It's the most common isotope of hydrogen. If we add a neutron to that, then it still has the same chemical properties because it still has one electron, still has the same atomic number because it still has one proton. So those things haven't changed. It's still hydrogen because it still has the same atomic number, same chemical properties. The only thing that's changed is the atomic mass. This has a mass of 2, and so we call it hydrogen 2 or deuterium. As I said before, those both exist in nature, and there's about 99 hydrogen 1 atoms for every hydrogen 2 atoms that we're going to find in nature. And so that's where we got the average atomic mass of hydrogen is 1.01, remember on a previous slide. The third isotope of hydrogen wasn't known until we had nuclear reactors because it's a man-made isotope of hydrogen. It's called hydrogen 3 or tritium. So see, protium is hydrogen 1, even though we don't use that name very often. Deuterium or 2 is hydrogen 2, and tritium or 3 is hydrogen 3. Hydrogen 3 then must have one electron, which gives it its chemical properties, has one proton, which gives it its atomic number. Both of those things say it's a hydrogen atom, but the only difference is that it has 2 neutrons, so now it has an atomic mass of 3. The 2 neutrons plus the proton make up an atomic mass of 3. So we call that hydrogen 3 or tritium, and all these pictured on this slide from left to right, protium or hydrogen 1, deuterium or hydrogen 2, and tritium or hydrogen 3 are all different isotopes of hydrogen. So isotopes are atoms that differ in the number of neutrons that we find in the atom. The atomic mass that we listed in the periodic table, as we saw earlier when we were studying each block of the periodic table, is the average of the atomic masses of all naturally occurring isotopes. So for example, I can work back and forth between the periodic table and nature and get the same information out of both. So looking at the periodic table, I see that underneath the iron symbol is an atomic mass of 55.845, 55.845. That's the average atomic mass of all the naturally occurring isotopes. Because this number is closest to 56, we're going to guess that 56 is the most common isotope of iron. We look down the left side of the table and it shows the percentages of each atomic mass. Turns out 91.7% of the iron in the universe is, or at least on Earth, is atomic mass 56, and so that jives with what we know already because the average atomic mass of iron is close to 56. The other atomic masses that are represented in iron on Earth are 54, 57, and 58, but these occur at much lower proportions. And when we add all these up in a proportional way, looking at the proportion of these different atomic masses, we get 55.85 or 55.845, which is the number that's listed in the periodic table. If you work out the math that's in the table that I show here, you don't have to, but if it helps you to understand it by working out the math, you'll see that the math works out in this way, and that's where that number comes from. The basic information that you need going into the exam and going into the rest of this course is that 55.845 is close to 56. And so 55.845 tells us that the most common isotope of iron is atomic mass 56. That's what you need to know. That's what you must know. Everything else that I explained and all the mathematics that goes into that is in the nice to know category, not in the need to know category. Another thing that's in the need to know category are these three isotopes of hydrogen that we talked about. Hydrogen, or protium, deuterium, and tritium, and how they differ, what the difference is between those three isotopes of hydrogen. Next, in the next objective, we'll turn to radioisotopes. And it turns out that some combinations of protons and neutrons are unstable. Sometimes that instability is reflected in the fact that the nucleus of the atom comes completely apart. And we'll look at an example of that, not from the human body, but from nature, and it's something we use to diagnose and treat illnesses in the human body, so it's still going to be important to us when we use radioisotopes in medicine. When this nucleus of the atom comes apart, we call that nuclear fission. Fission describes the breaking apart of something. And so nuclear fission is when the nucleus of the atom breaks apart. Sometimes it's not that violent. Sometimes we get energy out of an atom and it becomes a radioisotope just by a mere rearrangement of the protons and the neutrons in the nucleus of the atom, or a particle is given off from the nucleus of the atom. Those are still radioisotopes, just not as dramatic as the idea of the nucleus actually splitting apart. So uranium is an example of an atom where the nucleus comes apart. And so in uranium-235, which is the kind that we use in atomic weapons or in nuclear reactors, the reason these work in atomic weapons or in nuclear reactors for uranium-235 is that when they're struck by a neutron, then they become briefly, for just a nanosecond, for a very, very brief period of time, they become the atomic nucleus, which has 236 particles in it, or 236U. And that's an extremely unstable nucleus. It's an arrangement that can't be sustained for very long. And so that nucleus breaks apart. As it breaks apart, it makes 3 more neutrons and 2 nuclei. And the nuclei have varying mass numbers. They'll add up to atomic mass of 233 because we took 236, we subtracted off the 3 neutrons. And so they'll have to add up to 233, but they split apart in different ways in something that sums up to 233. So for example, one could be 100, the other one could be 133. One could be 98, 102, the other one could be 131, and we'll see an example of that a little bit later on. But as uranium splits, it becomes 2 nuclei and 3 neutrons. Now these neutrons that we see released here on the right-hand side of the diagram are flying off with a great deal of energy out of this nucleus as it splits apart, and these can then impact other atoms of uranium-235. So now going back over to the left-hand side of the diagram, these become neutrons which then impact, which then collide with the nuclei of other uranium-235 atoms. The uranium-235 nucleus, when the neutron hits it, turns into the unstable uranium-236, which then splits apart, releasing 3 neutrons and 2 nuclei of varying molecular or varying atomic weights. You can see how this becomes a chain reaction very rapidly. This is the nuclear chain reaction that we see in nuclear reactors that releases a great deal of energy. This is the nuclear chain reaction we see in atomic bombs, in what are called fission bombs because they use nuclear fission. So the atomic bomb that was dropped on Hiroshima was an example of this atomic bomb design where uranium nuclei are going to break apart when they're impacted by neutrons. That's going to make more neutrons, which are then going to then impact more uranium nuclei, and so on and so forth. And so we get a nuclear chain reaction until we run out of fuel. That's what makes these chain reactions so powerful. Well, when that happens, and depending on when you're listening to this video, this is either a fairly recent event or a fairly remote event, but you may remember that at some point in the past that there was a nuclear reactor in Japan that was hit by a tsunami, and that destroyed the ability to add cooling water to the reactor. In the absence of cooling water, then neutrons were able to strike uranium-235 atoms, and this reactor started to go critical, started to melt down. And one of the things that we were worried about, especially in the Hawaiian Islands, was iodine-131. You may remember on an earlier slide we saw iodine-131 as one of the atoms that's used in nuclear medicine. In nuclear medicine, in humans, we use iodine-131 because it concentrates in the thyroid. Remember, if we go back to our table of what iodine is used for making thyroid hormone. It concentrates in the thyroid gland. Iodine-131 can be used to destroy the cells in the thyroid gland because it concentrates there. So we use that in patients for something called a radioablation, where we're actually destroying their thyroid tissue when their thyroid is overactive or they have too much thyroid hormone. Then we're destroying thyroid tissue with this radioactive isotope. But in children, especially, we don't want to destroy their thyroid with iodine-131. If they get exposed to iodine-131, which is one of the byproducts of this nuclear reaction, remember uranium-236 splitting off 3 neutrons, that gives us a total number of atomic particles, protons and neutrons of 233. 131 of these are iodine, and 102 of them are something else. So this is a radioisotope that's formed as a product, a byproduct of uranium nuclear fission. That iodine-131 then gets into the environment. This is a gas. It goes up into the clouds. Then it becomes part of the environment. It gets rained down as fallout. It doesn't have to be a caribou. It doesn't have to be in the Arctic. It can be just cows, as we'll see in just a minute. It doesn't have to be an Eskimo. It can be you or I. And the Eskimo and the wolf, by consuming the caribou, are going to get the iodine-131, which originally came from the environment, and it came from the environment because a nuclear reactor released it into the environment, or a nuclear weapons explosion. We can get that iodine-131 in cow milk, and that cow milk can have levels of iodine-131 that are unsafe, and that's why the Environmental Protection Agency and the FDA monitor levels of iodine-131 in cow milk. So we can see that there are many, many different sources of environmental radioactivity. The largest source of environmental radioactivity is in this area is radon. Radon is a radioactive gas that concentrates in homes, especially in basement areas, and as people breathe that in, then their lungs are exposed to radioactivity. Chernobyl evacuees also got a large dose of environmental radioactivity. The natural and background radioactivity is a little bit less than that, and then medical X-rays, the radioactivity that you generate as a person from the radioactive isotopes that are in your body, and from nuclear power and weapons testing, as you can see here, are much less. This is a log scale, which means it goes by powers of 10. So the radiation dose from nuclear power and weapons testing is about 1/1000th of what people get from radon exposure in their home. Well, in this part of the United States, there was actually a lot of iodine-131 exposure from above-ground nuclear testing that was done in the 1950s. And the people that lived downwind from this nuclear testing were called, naturally enough, downwinders. And it turns out that these people obtained a pretty good dose of iodine-131 to their thyroids. They have a higher incidence of thyroid cancer. They have a higher incidence of other kinds of cancer from other kinds of environmental radioactivity that they were exposed to. But this map is just showing us iodine-131. So this is from the National Cancer Institute, and it's data for each county in Utah or in Nevada or in Wyoming or any other state that you happen to reside in 1958, and I picked this because that was the year that I was born in. So at that time, the area I was born happens to be in one of the green areas, and so I didn't get a large exposure to environmental radioactivity. But people who were born and grew up and were drinking milk in the areas that are shown here in red got a huge exposure to iodine-131, radioactive iodine, from above-ground nuclear testing during that time. Well, we use these isotopes not just in this kind of theoretical sense of things that happen because of people testing nuclear weapons or because of nuclear reactor accidents, but we use these in our patients in nuclear medicine. And the particles that we use in nuclear medicine are shown in this table. So we may use neutrons, we may use protons, we may use beta particles, which is just a way of saying electrons. Just as an aside, remember that we show the atomic mass up here, which is a mass of 0, and we show the charge or atomic number down here, which is 1 electron, so it's -1. We show the mass number of a positron, which is just an antimatter form of electrons, or a positive electron, as a mass of 0. That's the A, the superscript, and then the atomic number is a positive 1 because it has a positive charge. So it's called a positron or a positive electron. When we use that in nuclear medicine, we might use a technique called positron emission tomography to be able to look at slices, tomography of the brain with the emission of positrons. And where there's a lot of positrons, we see an orange or a yellow color. Where there's not very many positrons, we see a deep blue color. And by positron emission tomography, we can map out the chemistry of different areas of the brain. We use this for diagnostic techniques. We may use alpha particles, or we may use a heavy hydrogen nucleus, which is called a deuteron. Remember, we saw that as deuterium if we had the nucleus plus the electron that surrounded it. So alpha particles are helium nuclei, as we saw earlier. Beta particles are electrons, and a gamma particle is a high-energy photon. This comes from the rearrangement or the decay of the nucleus. A photon is given off. We're going to look at photons in the next objective. These come out of the nuclei. Photons have no charge and no measurable mass. So we're going to talk about photons next as we segue into talking about the different forms of electromagnetic energy. So what we're going to see as gamma radiation is merely a high energy photon. So if you have a photon that has a lot of energy to it, then that's called gamma radiation or X-rays. The protons rearrange and adopt a lower energy state, emit a photon, and as they do so, that photon that's given off can penetrate things because it has a lot of energy. And so that high energy photon is also called a gamma ray or an X-ray.